here's what I want to remind you about. There are basically three versions of 2 to the x power, okay? We can understand 2 to the x power if we look at 2 to the x power when x is equal to 0, when x is a positive number, and when x is a negative number, okay? So those three situations give us basically a very different idea, okay? Because, for example, if we say 0, if we say, well, what is f of 0? Well, that's 2 to the 0 power, and what's anything to the 0 power? Is 1, okay? And so that's the first interesting thing, is that where with polynomials, when we plug in 0, our answer is whatever our constant is. But here, what's our constant? Well, it's, so what's added on the end here? 0. It's plus 0, right? Yeah, so 2 to the x is the same thing as 2 to the x plus 0. We're adding nothing on, okay? And so what we might think, let's say we were adding something on. Let's say that we were adding on 5, okay? Well, the answer wouldn't be 5. It would actually be 6. So the answer to the answer to an exponential function, when you plug 0 in, becomes, well, assuming there's no negative up front, it becomes 1 larger than what you have come to expect in polynomials, okay? So when the constant is 0, f of 0 is actually equal to 1 because 2 to the 0 power is 1, okay? Now, what happens when x gets larger? What do I mean by x gets larger? Can somebody give me an example of x getting larger?
5?
Yeah, greater than 0. 5, sure. Okay, as it goes 1, 2, 3, 4, 5, 6, 7, 8. Got it? Or even 30, 40, 50, 60. Okay? As x gets larger, this 2 to the x, so 2 to the first is equal to 2. 2 to the second is equal to 4. 2 to the third is equal to 8. We're doubling. 2 to the fourth is 16. So when x gets larger, what happens to y? It doubles. It gets larger, 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 right? Okay? So larger x means larger y, okay? Approaching what? What's this eventually going to get close to? Infinity. It's approaching infinity, okay? So it grows without bound, okay? But what happens when x gets smaller? Now, when I say gets smaller, I mean it goes negative, because we already said what happens when x is 0. So when we're on the positive side of 0, 2 to the x just grows without bound. But I want to remind you what happens when x goes negative. When we go to -1, -2, -3. So 2 to the -1 power, if you recall, is 1 over 2 to the first power, which is 1/2. Right? And then 2 to the -2 power is 1 over 2 squared, which is 1/4. 2 to the -3 power is 1 over 2 to the third power, which is 1/8. And then it'll become 1/16, 1/32, 1/64, 1/128.
So an exponential function can't be negative unless
That's correct. Unless it starts, yes, unless there's a constant that subtracts, or unless it starts with a negative in front of it.
So the line just gets closer and closer to 0.
That's correct. It just gets closer and closer to 0. Okay? So in one direction, it grows without bound. In the other direction, it shrinks with bound. It gets closer and closer to 0. Okay? And what that looks like graphically looks like this. So this is the basic shape of an exponential function. We know that when x is 0, the y-intercept, when x is 0, it's going to always go through the point 0, 1. Okay? So this is going to be 0, 1. Okay? So it's going to pass through this point. On the positive side, it's going to grow without bound. It's going to grow without bound. Okay? So up and up, arrow up. Okay? But as x becomes negative, it does shrink. It gets smaller and smaller, but it's bounded by 0. So it gets closer and closer to 0 without actually touching 0. It essentially goes sideways is what it does. It essentially goes sideways. We call that a horizontal asymptote. So what you're looking at here, this shape where we're flat on the left, but we're steep on the right, and we pass through the point 0, 1, that's an exponential function. Okay. That's an exponential function. And it's very different, fundamentally different than a polynomial. And so I want to show you how to graph these and variations of them. Okay? All right, so, and I'm going to try, because I don't actually have a procedure written out step by step, so I'm going to try and build a procedure as we go. I'm going to try and build a step-by-step procedure of how I would approach it if you handed me an exponential function. Okay? So let's look at this worksheet that I gave you. Let's look at question number 1. It says, sketch a graph of 3 to the x power. Okay, so f of x is equal to 3 to the x power. I'm going to draw a coordinate plane, a rough coordinate plane. No grids, no labels. Now, there is something important on here. I think we should be putting the x and the y coordinate. I should be putting the x and the y label, because one element of this graph looks a lot like the x-axis, and I need you to know the difference, okay, when you're graphing them, okay? All right, so we want to graph 3 to the x power, okay? Well, the first thing you want to do is you want to plot f of 0, 1. Plot f of 0, right? We call that the y-intercept. The y-intercept. Okay? All right. So we want to plot the y-intercept, okay? Now, for 3 to the 0, it's real simple. We put a 0 in here, we get 1. And so in a circumstance, if there is no shift over here on the right-hand side, if there's no constant change, there's no like +7 or -3 or anything like that, then it's always, every single time going to pass through the point 0, 1. So we're going to put a point here, and we're going to label it 0, 1. That's the y-intercept. Now, it does not matter which exponential function it is. If it's positive in the front here, and it doesn't have any constant shift at all, it will always pass through the point 0, 1. If this said 12 to the x power, it would pass through the point 0, 1. Okay? All right, so that's the first thing we're going to do is we're going to plot f to the 0. The second thing we're going to do is we are going to plot f of 1. Okay? So f of 1 actually is a really interesting point, because f of 1 tells you the base of the exponent, okay? So like if I plug a 1 in here, what is 3 to the first power? It's 3, right? So what we wind up with is we wind up with the point 1, 3, which is maybe right about here. 1, 3, okay? And so here's the thing, is if you saw one of these, and instead of passing through 1, 3, let's say it passed through 1, 8, then it would be 8 to the x power instead of 3 to the x power. Okay? So this coordinate where it's 1 comma some number, that tells you the base of your exponent. Okay? Step 3, if there are any, and in this one there are not, plot the x-intercept. Okay, meaning the root. Okay. On a plain, typical exponential function, there cannot be more than one x-intercept. Now, if you start messing with this thing and put a cubic polynomial in the exponent, it'll give you some really strange shapes, and it could cross the x-axis several times. Okay? This particular one does not have an x-intercept, so I'm going to make a note here. If no constant, or if let's say if the constant is 0, or if constant is 0, there isn't one. So this particular graph will not have an x-intercept. We'll go ahead and put step 4. Sketch, now this is, I'm going to have to explain this one. Sketch the horizontal asymptote, which you can technically do first if you want to. The horizontal asymptote is, let's see, a horizontal line. Let's call it a horizontal dashed line. We're gonna make a dashed line. Line at y equals the constant. Meaning, whatever the constant is on the function, okay? Whatever the plus c is on the end, that's where your horizontal asymptote is. Y equals means a horizontal line. Y equals 5 would be a horizontal line up at 5, where y equals 5. Horizontal line at y equals 5. Y equals -3 would be a horizontal line down at -3. It would go sideways, okay? In this case, where is the horizontal asymptote? It's at 0 because there is no constant. And so I'm going to go ahead and graph at 0. Watch what I'm going to do here. Right on the x-axis, I'm sketching a dashed horizontal line. This is the horizontal asymptote. What is the purpose of the horizontal asymptote? That is the 0 that the graph is getting closer and closer and closer and closer to. Okay? But it never actually touches it. Never actually reaches 0. Okay? So we've got our horizontal asymptote. We've got our y-intercept. We've got this point 1 comma 3 or whatever it would be. Okay? Then we can, and if there was an x-intercept, we would have that also. But we don't have that. Okay? And so now what we're going to do is we're going to, let me think about how to do this. Starting at the y-intercept. Sketch backwards. Moving slowly. I say slowly, that's probably not the right word, but that's the first thing I can think of. Toward the asymptote. Let me show you what I mean by that. I'll let you write that down and then I'll show you what I mean. So starting at the y-intercept, sketch backwards, moving slowly toward the asymptote. What you're doing is this, is the asymptote is like, there's like a gravitational pull toward it. But there's also a, you don't cross it and you don't touch it. Let me show you what I'm going to do. Okay? Very slowly and flattening out. I'm just going to get closer and closer to the asymptote. Do you see that? I'm going to put getting flatter and flatter. Getting flatter as you go. Okay? And this part of the graph represents the 1 over 2, 1 over 4, 1 over 8, 1 over 16, 1 over 32, 1 over 128, 1 over 256, 1 over 512, 1 over 1,000, 1 over 2,000, 1 over 4,000, 1 over 8,000. It's never actually going to touch 0. It's just going to get flatter and flatter. It's going to get more and more minuscule. Okay? But it's still going to be a positive number. It will always be a positive number. Okay? This is the limit as x approaches negative infinity. Okay? So the limit of the function as x approaches negative infinity is 0. Okay? Now, the other direction, starting at the, so now 6, starting at the y-intercept, again, we're going to do the forward direction. At the y-intercept, sketch forward. Passing through plotted points passing through plotted points and becoming steeper and becoming steeper. So that's a really funny thing about an exponential function is one direction, typically toward negative infinity, it becomes flatter, but going towards positive infinity, it becomes steeper, 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 steeper. Okay? We have a name for this kind of a function. It's called a strictly increasing function. Because when we start all the way over here, technically, isn't it actually getting steeper from over here? Right? Steeper, 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 steeper. Exponential functions, that's what they do, is they become infinitely steeper. You may think, doesn't that mean that eventually it goes vertical? Nope. It never actually goes vertical. It just becomes infinitely steeper. Yep. The slope becomes 1,000, then the slope becomes 2,000, then 4,000. Eventually the slope becomes 1,000,000, then 2,000,000, then 4,000,000, 8,000,000. The slope eventually becomes 1,000,000,000. It never actually goes vertical. It just gets steeper and steeper through infinity. Okay? So here's what we're going to do. We're going to pass through this point, and we're getting steeper. I didn't quite get it. There we go. Steeper, steeper, and there we go. We're done. And I'll put a little arrowhead on each of these. There we go. There's an exponential function. Okay? Nope, not on these. Yeah, see, that's the thing. Only when it goes perfectly vertical, I guess you could say, that's when you have a vertical asymptote. And that's what's so interesting, or what I find interesting about exponential functions, is they don't have vertical asymptotes. They look like they should, but they don't. This graph exists continuous from here, even at x equals 5 million. It's just an insanely large number, well, compared to what we're accustomed to. 2 to the 1 million power. It's continuous. It's there. Okay. All right. So I'm thinking what we'll do is, you guys want to try question number 2? Yeah. You guys want to try graph number 2? Mm-hmm. All right, go for it. I'll give you a minute or two. So we're graphing what? 4 to the x? All right. Can I get everybody's attention? Yep. Yes. All right. Can everybody watch? Ready? Ta-da! It's the exact same thing. It still passes through 0, 1. It still has the horizontal asymptote at 0. It still flattens out to the left. The only difference is that it passes through the 0.14 instead of the 0.13. Same graph. Okay? I believe we did have that conversation in Unit 3 about the fact that exponential functions really only differ in their base. You know, other than that, almost. Now we are going to see in a couple of examples now how you have to be able to know. But I do want to point something out. Okay. Please, if you're trying to figure out, so let's say you're looking at the graph of an exponential function and you're trying to figure out what the base is, what the constant is, okay? Here's what you need to understand, a couple of facts. The first fact is this, okay, is that the y-intercept is always 1 unit away from the horizontal asymptote, okay? So make that a note. Just a couple facts about exponentials, okay? 1, the y-intercept is always, now I say always, understand, if we start really messing with this thing, with this exponential function, some of these facts will change. We are only working with basic exponential functions today.
Are there any more steps? Is it
Oh, no, so hang on, plot that. Yep. No, this is it. Oh, yeah, this is pretty much it, yeah.
Okay.
Other than these facts, yeah. The y-intercept is always 1 unit vertical away from the asymptote. Always 1 unit vertical away from the asymptote, okay? So if your asymptote is at y equals 7, then your y-intercept it's going to be 0, 8 if you're above the asymptote, or it'll be 0, 6 if you're below. You might be like, what in the world? That's obviously above. We're about to see a situation where your exponential function is below the asymptote, okay? And that's when you have a negative on the front of the exponential function, okay? But you're always 1 unit away. If your asymptote's at 7, then your y-intercept is either at 8 or 6. If your asymptote is at -3, then your y-intercept is either at -2 or -4, okay? So that's one of the first things, one of the first facts you need to understand. The second fact is this, okay, is the f of 1 point, okay, is always a distance equal to the base, the exponential base. The f1 point is always a distance equal to the base from the asymptote. Right? So look, the asymptote here is at 0. The f of 1 point, f of 1 is equal to 4. That's 4 units away from the asymptote. So if your asymptote is at 0 and your base is 4, then you're either at 1, 4 or you're at 1, -4. If your asymptote is at 11, up here, if your asymptote is up here at 11, okay, and your base is 5, then your f of 1 is either at 16 or it's at 6. Okay? We're going to see that. Okay, that's important. The reason I'm giving you these facts is so that you understand when you're looking at a graph and trying to figure out what the function is, you're mainly going to be looking at the f of 1 point and the f of 0 point. The f of 1 point and the f of 0 point essentially define the function, okay? All right, I think with this information, we can now do almost any problem. Can I do an example for you? You don't have to do it, but you can watch me do it, where what I'm going to do is I'm simply going to identify a function given just 2 points, okay? Just given Just 2 points. No picture, no function. I'm going to show you how I can find what the exponential function is. What's that?
What you mean?
Let me do it first, then I think you'll see what I mean. Okay? It's going to be based on these two facts. Okay? All right, cool. All right, so I'm going to erase everything. Now, what I'm about to do, I am not going to expect you to do on the test. Understand? So what I'm about to do, I'm going to do strictly for the sake of learning, not because I'm going to have you do it on the test. So watch this. So let's say that I know that the graph passes through the point 0, 4. Okay? I know that the exponential function passes through the point 0, 4, and it also passes through the point 1, 6. Okay? So first of all, I know that it doesn't have a negative at the beginning of it. I know for sure it doesn't have a negative at the beginning. If it had a negative at the beginning, so you'll see in just a little bit, when it has a negative at the beginning, it has a shape that looks like this. It's below. And so the y-intercept is higher than the f of 1 point. Do you see that? So this point is lower. Do you guys know what I mean by lower? Go ahead, Michaela.
The f of 1 is the second.
The second point, that's correct. Yep. See how this f of 1 point is at a lower y level than the y-intercept? See what I mean? That's immediately tells me that I must be below the, or it must be a negative exponential curve, okay? Because if it was a positive exponential curve, wouldn't this second point actually be above, right? But since my y-intercept is 4 and my f of 1 point is 6, doesn't that indicate that I'm upward sloping, I'm increasing? Therefore, my exponential curve must be a positive exponential curve. It does not have a negative at the beginning of it, okay? All right, with me so far? All right, here's the other thing. So now that I know that it's definitely upward sloping, I know that my curve is above the asymptote. It's above the asymptote. Now I want to find out where the asymptote is.
The asymptote
Go ahead.
is like the invisible line.
That's correct. The dashed one, that green dashed one that I did, that's actually invisible even though I revealed it with green paint. Yeah. So anyway, what does the fact say about the y-intercept and the asymptote?
It's always vertical.
It's always 1 unit vertically away, right? 1 unit vertically away. And I know that this graph is above the asymptote. So that means that this point 4 is 1 unit above the asymptote. And so where must the asymptote be?
Like right above 0.
No, specifically, where is it? It's 1 unit away from 4.
Oh, 3?
It's a 3. I know that. Because this is upward sloping, that means it's above the asymptote. And that means that I'm definitely, and since this has to be 1 unit away, it must be 3. Do you guys see that?
So if it were the other way around, if it were negative,
Yep.
then it would be 5.
That's correct, then it would be 5. That's exactly right, okay? So here's what that means. What that means is that I'm going to have something here to the x power, but here's what, because the asymptote is at 3, that means that the constant is 3. Whatever the constant is what the asymptote is. All right, is everybody with me? Are you with me on this? Okay, cool. So now all I have to do is find out what the base is and I'm done, right? Well, how do I find out the base? Well, how much higher than the asymptote is my f of 1 point?
A distance equal to the base from the asymptote.
Correct, and I want to know what the base is.
Right.
So how far is this away from this?
3.
3. That must mean that the base is 3.
Wait. So if it's negative, then point should be negative 2, right?
Yeah. No, not necessarily. So you know what? Let's do another one. Let's do another one, just so that you can get the idea here. Okay, let's say that this exponential curve passes through the point 0, 7, and it also passes through the point 1, 6. Again, it's passing through 1, 6. So watch this, Michaela. Because I'm going from a higher point to a lower point. So 0, 7, okay, is on a coordinate plane. 0, 7 is here, right? Let's say this is 0, 7, okay? Where is 1, 6? Wouldn't I have to go here and then up 6? Well, is this point going to be above the 0, 7 or below the 0, 7? Below, because 6 is less than 7, right? What does that automatically mean must be happening to my exponential curve? It's negative. It's a negative exponential curve. That's right. Now that I know that it's a negative exponential curve, and I know that the y-intercept has to be 1 unit away from the asymptote, what must the asymptote be?
If it's negative, so it'd be 8.
8, yes. So I know that my function is going to be f of x is equal to some base to the x power plus 8. Right? Now, Michaela, how far away is 6 from 8? 2. So that means that the exponential base is 2. But it's upside down. It's negative, so not just 2, but negative 2. Negative 2. Now, I need to be clear. The base is not negative 2. The base is 2, but we're putting a negative, we're multiplying it by negative 1. It is not negative 2 to the x power. I want to be very clear on this. This is a whacked out, not continuous, weird function. Okay? This is weird. We don't do this in a regular, this is for a higher level math class in college, okay? All right, what you got?
When the line, what's the line called again?
Asymptote?
The asymptote, no, not the invisible line.
Oh, the curve. The curve itself, yeah.
When the curve is negative, the base will be negative?
You will see a negative in front of the base, yes. So if the base is 2, you'll see a negative in front of the 2. In fact, should we go ahead and look at question number 4?
Yeah.
Let's do number 4, shall we?
Wait, how do we do 3?
Okay, good question. Let's do 3. Everybody, can we try 3? You guys walk me through the procedure that I gave you. Our function is what? E to the x? So f of x is equal to e to the x. I'll draw a coordinate plane. What should I do first? Okay? Yeah, f of 0. And if I put a 0 in here, what's e to the 0 power? 1. So once again, it's passing through the point 0, 1. Once again, 0, 1. Okay? Now, pause for a second. Michaela, I think you'll find this very interesting. What if there was a negative in front of the e?
Then it'll go down.
Right, so if I put a 0 in here, e to the 0 power is 1. But now I have to make it negative. If there was a negative in front of it, it would be negative 1. Instead of 0, 1, I would have 0, negative 1. That's correct. And we'd be below the x-axis. We're going to see that in a couple minutes, okay? For now, let's stick with our 0, 1, okay? All right, what's our second point going to be? Plot f of 1. Now, if I put a 1 there, won't I have e to the first power? Hold on tight. Let me tell you what e to the first power is. It's e. So we're not dealing in what the approximate number is. We're just going to call it e. So we're going to plot the point 1e. Now, e is close to 3. It's between 2 and 3, closer to 3. It's 2.71828, okay? So just somewhere, although we're not using a grid, all we have to know is e larger than 1, equal to 1, or smaller than 1? It's larger, so we're going to go above the 1, right? So we're going to go up here at 1. We're going to put a dot, and we're just going to call it 1, comma, e. That's all we're going to call it, 1e. Okay. And now we're going to put in our asymptote. Let's do brown this time. Doop, 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 doop. At 0, right? Right? Yes. That's very good. Yep. I heard what you said. You said it's roughly equal to, and then you said? Yes. Very good. That's exactly right. Honestly, if you really want, you just say 2.7. It's roughly equal to 2.7.
So
Yep. Yeah.
If it was negative, it'd be flipped down.
That's correct. Exactly. And so now all we got to do is draw our curve. Now, oh, by the way, is there an x-intercept? No, there's not, because look, if our curve, in order for there to be an x-intercept, our curve has to cross over the x-axis. When the asymptote is, let me show you some examples of it crossing. Look, let's say that our asymptote was down below the x-axis. Let's say this was our asymptote, and this was our curve. Now is there an x-intercept? Yeah, right here. We're going to get to that in a couple of minutes. We're going to do one of those in a few minutes, okay? That's where it crosses over the x-axis.
Okay, I
Yep.
have another question.
Okay?
Like, I know you answered it.
It's okay.
But how do we, like, the asymptote, how do we know that?
It's whatever the constant is.
Okay, like, plus whatever.
Yep, plus whatever. But because all the ones we've done so far have been plus 0, we keep putting it at 0.
Okay.
But look down the page. You'll see that there are several where it's not plus 0. Okay?
Mm-hmm.
And on those, yeah, Kendall. Yeah, go ahead. Okay, so now let's go ahead and sketch our curve. Is that okay? So we're going to go backwards, back flatter, right? Back flat, forward steep. Put some arrowheads. How's that look? Pretty good? There we go. Yep. Listen, the main thing you need to know about exponential functions is this, is they approach 0, for lack of a better way of saying it, as you go negative. Okay? They take a long time to become 0. But they become infinity, not infinity, but they become big numbers really fast. Okay? They in a very small number of x's, that steepness goes nuts. Okay? Do you see this graph right here? This is the graph of a retirement fund. That's what you're looking at here. This is the graph of a retirement fund. This is one of the reasons why they tell people when they're young to put their money in IRAs, mutual funds, and other kinds of investment accounts. Because investment accounts grow exponentially. They double, then they double, then they double, then they double. Now, they take 7 or 8 years to double. But consider this. If you put $5,000 in the bank when you're 18 years old, I say in the bank, I mean in a mutual fund, in an investment account, when you're 18 years old, and let's say that every 8 years it doubles, okay? So that means when you're 26, it's now 10,000. That's at, so 18, then at 26, it's 10,000, okay? Then at 34, it's 20,000. Then at 42, it's 40,000. Then when you're 50, it's 80,000. Then when you're 58, you're still working, it's 160,000. And let's say you're about ready to retire when you're 64, it's 320,000. So you're 5,000. Now listen, this is not I put 5,000 in the bank every single year. I'm saying one time when you were 18, you put 5,000 in an investment account, and now that you're 64, you got $320,000 to spend. You know what happens if you then put $5,000 in the same account when you're 19? Then when you're 65 years old, you'll have another $320,000 to spend. And this is why they recommend you start young. Now, what if you don't start until you're 36? Okay? Then when you're 44, you have 10,000. Then when you're 52, you have 20,000. Then when you're 60, you have 40,000. And when you're 68, you have 80,000. Big difference between 80,000 and 320,000. Okay? So if when you're 18, you put 5,000 in an IRA. Then when you're 19, you put 5,000 in an IRA. Then when you're 20, you put 5,000 in an IRA. Then when you hit 64, every year for the rest of your life, your income will be $320,000. Pretty cool, huh? Right? Okay? So, but most people don't think about how important this is until they're in their late 20s. They're like, oh, I'll do that later. No, that's the whole point. You just lost years of doubling. Now, I'm not encouraging people to be like addicted to money. That's not the point here, okay? You know what else grows exponentially? What's that? Well, diseases. Diseases grow exponentially. They were able to estimate how many people would have COVID by certain dates based on exponential models. Okay? Right? So think about zombies, right? Today there's one zombie. Tomorrow there's two zombies. If each zombie makes one zombie per day by biting a human or scratching a human, then after 3 days, right, we have 8 zombies. And after 4 days, 16 zombies. Then 32 zombies. Then 64 zombies. You wonder why after 2 weeks, it took them 2 weeks. They were like, oh, there weren't that many of them. And then after 2 weeks, there's like 17,000 zombies walking around. How did that happen so fast? Exponential growth. Exponential growth. They hit that steep curve right there. Yep. Zombies. Now, I mean, I'm not saying there's really zombies, but there is really COVID, and there is really Ebola, and there is really other kinds of diseases that grow exponentially. All right, so can we try a couple more now? Do one where it's where it's negative, and then we'll do one where we plus or minus. Is that cool? All right. Let's do number 3 or 4. Should we do 4? What do we got? Negative 2 to the x power. We're going to do it the exact same way. We got negative 2 to the x power. We got our graph. What's the first thing we graph? F of 0. If I put a 0 in here, what's 2 to the 0 power? 1, except that now it's negative, so it's negative 1. So now we're plotting the point 0, negative 1. That's down here. We're not plotting 0, 1. We're plotting 0, negative 1. So this is going to be 0, comma, negative 1. There we go. Okay. And now what do we do second? F of 1. That's right. So if I put a 1 here, 2 to the first power is 2, but it's negative now, right? So now we're plotting 1, negative 2, right? So here's 1, and we're going to go down to negative 2, which is right here, and we're plotting the point 1, comma, negative 2. And now we're below. Where's the asymptote at? There's nothing over here, right, except a 0, right? So we're gonna do a horizontal asymptote at 0 again. So where does it look like our points are? Are they above or below? Below. They're below. So watch what we're going to do. There's no x-intercept. Again, if the asymptote is at 0, there's no x-intercepts. Okay? All right, now watch this. We're going to go backwards, and we're going to get flatter. Note that I said backwards flatter, right? Toward the asymptote. Did I say backwards down? No, I said backwards toward the asymptote, which could be up. But it's got to become flatter, right? So watch this. Backwards toward the asymptote and flatter. You see that? Backwards towards the asymptote, flatter. I'll go ahead and throw an arrow on there. You can do it later. I'll do it now. And then what did we do forward? Forward through the points and steeper. Steeper could mean down, steeper. Okay? Forward through the points and steeper. There we go. There's our negative 2 to the x.
Doesn't matter how steep you make it.
Nope. Yep. I mean, if you make it steep, I know which side you're on, right? Because one side's flat, the other side's steep.
Okay.
Yep. And it could even be really ugly. I don't care. Okay? Yeah.
Why do you keep marking 1 on the x-axis?
Right here?
No, like on the...
Oh, I don't know. You don't have to do that. I do it because, like, I know that the first important point is on the y-axis. The second important point is where x is equal to 1. That's the only reason I'm doing that, but you don't have to do that. You can just move over and put a dot at approximately 1, comma, negative 2. But you do understand that that is associated with that, right? Okay, good. There we go. You don't have to mark that. Okay. Are we now ready to do one that has an x-intercept? Okay. All right, let's do it. All right. So I think question 6 or 7, maybe 7. 7. Let's do 7. 3 to the x minus 7. 3 to the x minus 7. Okay, so now we're going to have an x-intercept and our asymptote. Oh, no, I'm sorry. Yeah, minus 7. Our asymptote will not be on the y-axis. So we're doing positive 3 to the x minus 7. All right, so step 1, plot f of 0, right? So if I put a 0 in here, what's 3 to the 0 power? 1. And what's 1 minus 7? Negative 6. So my y-intercept is at 0, negative 6. So it's all the way down here. So I'm going to put a dot, and I know that that's going to be 0 and negative 6. 0, comma, negative 6. What's the step 2? Is that the y, the 1? Plot the 1, right? Okay. So if I put a 1 in here, what's 3 to the first power? 3. And what's 3 minus 7? Negative 4. So I'm going to 1 and then down negative 4, right? So it'll be like maybe right here. Does that look okay, guys? And we're going to call that one 1, comma, negative 4. Do you notice how the negative 4 is higher up than negative 6? So we know that it's an upward slope, that it's a steep up, not a steep down. Okay. Now, what's the next thing say? Asymptote, right? Oh, the x-intercept. We got to do the x-intercept now. Okay. I forgot about that. I forgot. I was ready with you. Okay, we got to do the x. Okay, so now, how do we find the x-intercept? Isn't it where the function is equal to 0? So here's what we have to do for step 3. We have to set the function equal to 0 and solve. I know, but it's actually really easy. It's not one of the hard ones. What can I do first? Yeah, I'll add 7 to both sides. So now I have 3 to the x is equal to 7. This is easy to solve. Don't I use a logarithm? Log base what?
Log base 3.
Yep, log base 3. So I'm going to do log base 3 over here and log base 3 over here. Log base 3 on both sides, right? Now, on the left side, it's going to cancel and leave me with just the x. The answer is simply log base 3 of 7. There's nowhere else to go. It's just log base 3 of 7. Now, let me show you what that looks like on the graph. So, log base 3 of 7, I happen to know, is larger than 1 because 7 is larger than 3. We learned that. Remember? Okay, good. So it's larger than 1. I also know that it's less than 2 because in order for it to be 2, this would have to be a 9. Okay? But really the only thing that matters is that it's larger than 1. That means that it is farther that way than this point. So I'm just going to put it over here if that's okay with you guys. I'm just going to put it over here.
We have to know.
Exactly where it goes? Or go ahead.
Yeah.
It just can't be wrong compared to these dots. Look, Michaela, here's the deal. If you got a dot here and a dot here, it's over here. You're not going backwards. Does that make sense? There could be another situation where it looks like this. Watch this, Michaela. Let's say your 0 point is here, your 1 point is here. Guess where the x-intercept is? In between.
Okay.
Does that make sense? It's going to be logical. In fact, if you want to, you can do steps 4, 5, and 6. Then go back and do 3 if you want to. You want me to show you what I mean by that? Okay. So what I'm going to do is, in this one that we're doing right now, I'm going to pretend that I didn't do the x-intercept, okay? Let's skip step 3, okay? I mean, we still need the number. We still have to do that, okay? But we're not going to put the dot, okay? Let's do step 4. What does step 4 say to do? Asymptote. Okay, so you ready? You want to make a note? If you need to make a note, that's the horizontal asymptote. Y equals whatever's right there.
So it'd be -7.
-7. Horizontal line at -7. Now note, we have a dot at -6. So do I have to go above this or below this?
Below.
Below, because I got to go below -6, right? And it doesn't matter where. I guess I'll put it right here. Is that good enough? I mean, it's a sketch. It does need to be horizontal. Don't make it a diagonal line. Am I going to get out a protractor and make sure that it's perpendicular to the y-axis? Nope. Just make it look kind of horizontal. Okay? Does that look okay? Does everybody think that that horizontal asymptote looks okay? All right, what's step 5 say, y'all? Starting at the y-axis. That's this dot right here. Yep. So should I go backwards first, right? So I'm going to go backwards flat, right, towards the asymptote. Is that okay? I know it's ugly. Is it okay, though?
Yeah.
All right, and then forward, I'm going to go ahead and pass through this 0.14, right? Right?
Yeah.
And then I'm going to go steep. All right, watch this. I'm going to go ahead and just go steep. You see that? And now I heard somebody say what I'm about to do. Who said it? Go ahead, tell me, Kendall. What am I about to do? Mark where it intersects. That's what I'm talking about, Michaela. I'm just going to go here, and wherever it happens to cross over the x-axis, that's where I'm going to put a dot.
So it doesn't matter. What do you?
This is a sketch, huh? We're going to label it. I'm going to show you that in just a second, okay? But do you see what I'm saying? That because we're sketching, do you remember when we were doing the sketches of the other things, we waited until after we drew the sketch and then we did the y-intercept? Because of how ugly it would have been is why, okay? So now that we've gone ahead and sketched this little line, man, this thing really, do I move around that much? I guess I do. Yeah. Okay, so watch this. You ready for the label? Here's the label. Don't freak out. The label is log base 3 of 7, comma 0. There it is. Log base 3 of 7, comma 0. Yeah.
So when we find what that is,
The x-intercept?
I think so. Yeah.
Yep.
Is it always gonna be in logarithm?
Yep.
Okay.
Every time.
So
You want to see something funny too? We didn't actually have to do this whole business over here. I was reminding you because we learned this in Unit 2. Okay? But every single time you can just see the base 3 and you can see the 7 here. And it's going to be log base this of that. But it's got to be positive.
okay. So whatever the base is
That's going to be the base of the logarithm. Yep.
okay.
Yep. And then whatever number is here. Now, if this is yeah, if it's positive, so here's the deal. It's really complicated. Don't write this down. I'm just going to tell you. Okay? If this and this are opposite signs, you have an x-intercept. If these are both the same sign, you don't have an x-intercept. Or, an x-intercept.
But they're opposite.
Right, so the thing is, this is telling you to shift down, this is telling you to go up.
Oh.
So you're going to cross the x-axis. If this told you to go down and this told you to shift up, you'd be shifting up and going down, so it would cross the x-axis. But if this tells you to shift down and this tells you to go down, you're not going to cross the x-axis. If this tells you to shift up and this tells you to go up, you're not going to cross the x-axis. Does that make sense? You don't have to write that down, but I'm handing it to you just sort of as these are the mathematical understandings that we develop the more we do math.
Okay, so how would we write it if it was positive?
Okay. If this said plus 7, so you're asking what would this whole graph look like if that said plus 7 instead of minus 7?
I think so.
Okay. Think about your question. I don't want to answer the wrong question.
Because I'm really asking just about the x-intercept.
Okay.
If it was positive, would it still be log 3 7?
Yep.
It would?
Yeah, so, but remember, one of these two would have to be negative. It would have to be negative 3 to the x plus 7.
Wait, so if the 3 was negative and the 7 was positive,
Yeah.
it would be log 3 of 7?
It still would, because let me show you what would happen. It's so cool. Watch this. What you would have is basically a reflection of what you're looking at right here. Your asymptote would be up here at 7. Your y-intercept would be at 0, 6. Your 1 point would be at 1, 4. And your 0 would be in the exact same place. And it would do that. Pretty cool, huh?
That's if the 3 was positive.
That's if the 3 was negative
Oh, okay.
and the 7 was positive. Yep.
Okay.
Yep. Look, negative curve, positive shift. Isn't that cool? I think it's cool.
Does that mean that log base 3 of 7 equals log base 3 of negative 7?
So here's the thing. Let me explain why that wouldn't happen. So if we had negative 3 to the x plus 7, right? If we set this equal to 0, we're not going to move the 7 over. We're going to move the negative 3 over, positive 3 to the x. See what I mean? And now it's log base 3 of 7 again. Exactly! Because one of them would be negative. Yep. Exactly. Yeah.
So
Yeah.
it doesn't matter the sign?
Yeah. Yeah, if both of these signs are opposite, you will have an x-intercept. If they're not opposite, you won't have an x-intercept.
Okay.
Yep. So now, again, that's just an understanding that I have mathematically. If you try to memorize that, it could mess you up. But if you memorized it enough, if you drilled it into your head enough, then maybe you would remember it. Okay? All right. Do you guys want to try this one on your own first? You want a couple minutes, or do you want me to jump right in? Jump right in. Okay. So what am I supposed to do first? F of 0. So I put a 0 here. What's 8 to the 0? It's got a negative on it now, so it's negative 1. Negative 1 plus 5? 4. So 0, 4. Somewhere around here, let's say. We'll call that 0, 4. Yeah.
Oh, okay, never mind.
We're going to call that 0, 4. Okay? Actually, it's probably, I don't think that's a good location for my label. I'm going to put the label over here. 0, 4. There we go. Okay. All right. What's the second point I should plot? F of 1. So if I put a 1 in here, 8 to the first power is 8, right? But it's negative, so now I'm negative 8. Negative 8 plus 5, negative 3. So that means I got to go to 1 and then down to negative 3. Let's say maybe right here. You might be thinking to yourself, Mr. Ryan, that point is a long way away from this point up here. All the ones we've seen so far, those 2 points are close, right? Do you know why they're so far apart?
Crosses the x-axis.
Well, it does, but there's a reason for it. Nope, not because it's negative. There's another explanation. Go ahead. That's right. The larger the base, the farther away these points are going to be. Do you guys see it? That 8 means that these 2 points are going to be 7 units away from each other. 7 units away. Yes, that's what it is. Yep. It's a vertical stretch. Did you guys hear what I said? 8 base means 7 units away.
Why
7 because this one is always 1 unit away from the asymptote, and this one is always base units away from the asymptote. Yeah.
Go down.
Down. Yes. Yeah, you guys got it. Isn't this awesome? Learning. Okay. What do you think?
Wait, that's what I... Wait.
It's at 5. Yep, it's at 5. Yeah. And not log base 8 of... That's right. That's exactly right.
That's the X, right?
That's going to be the x-intercept, right? But why don't we do that last instead of doing it third?
Okay.
Is that cool? But we know that it's going to be log base 8 of 5, right? Is everybody okay with that shortcut that they just used?
Yeah.
Does anybody have a question about it? So remember, our x-intercept is going to be log this base of this. Yes. Yep. All right, so look. Now let's go back. Somebody said asymptote at, what did you guys, somebody back there said 5?
Wait,
Okay.
would it be 5?
Yeah, so there it is. That's the asymptote. Because it's whatever the function says right there.
Oh, okay.
That tells us exactly where the asymptote is. Positive 5. Now, positive 5 is 1 unit up from 4, so it's going to be above. You see that? There's our asymptote. Bam.
Okay.
Pretty cool, huh? Right? All right. Now, given where these dots are, is it sort of self-explanatory where the curve is going to be? So we're going to go backwards and flat, right? Backwards and flat. Good. Forward, and then we're aiming for that point right there, right? So let's go kind of steep here. Is that okay? Was that all right? And now, wherever it crosses the x-axis, what are we going to name that point right there? That's right. That's the x-intercept. That's what it is.
And just the base is smaller than the constant?
Yes?
Constant, right?
The argument, yeah, sure. The constant, that's fine. I would call it the argument.
The base is smaller than...
Then the inside, let's say.
Yeah.